Swayam Prabha. Digital India. Educated India.
So, welcome back to the lectures on advanced calculus for engineers, and this is lecture number 8, and we will discuss mainly continuity in this lecture. So, the introduction to the continuity and then various problems, how to handle the continuity or how to show that the given function is continuous, the functions of two variables of course. And coming to the definition of the continuity, a function z is equal to f x y is said to be continuous at a point x naught y naught if this f x y is defined. So, of course, the function has to be defined, then only we can talk about the continuity of the function, and then this limit as x y goes to x naught y naught f x y, it should exist. And the third and the most important condition is that this limit should be equal to the functional value, to the equal to the function value here x naught y naught f at x naught y naught. So, the third condition is the most important one, because these two are of course obvious ones. F x y must be defined at this point, and the limit is already coming into the picture in this third point here, that the limit of this f x y when x y goes to x naught y naught, this should be equal to the function value at x naught y naught. So, if a function f x y is continuous at every point in a domain, then it is said to be continuous in that domain D. So, sometimes we have to prove that the function is continuous in a given domain D, then from each and every point, at each and every point, if the function is continuous, then we call that the function is continuous in that domain D. Coming to this continuity, so epsilon delta definition, because this is basically the limit. Here we need to prove that the limit is equal to the function value, or basically that limit is earlier we used to call that L. Now that L is the function value itself. So, this is precisely the limit definition only what we have. Instead of L, we will take now the function value at x naught y naught. So, a function z is equal to f x y is said to be continuous at a point x naught y naught if for a given epsilon there exists a number delta such that the difference between f x y and this f x naught y naught, because we are proving here that the limit of this f x y is f x naught y naught. So, the difference we have taken of the two f x y minus f x naught y naught less than epsilon wherever we take x from this delta neighborhood. That was the definition of limit also. So, here the only difference is that we have this function f x naught y naught instead of limit, and there we used to exclude that point, that because the function may not be defined at x naught y naught, still we can talk about the limit, but here the function has to be defined. So, therefore, this less than sign here or greater than this 0 is removed in this definition. So, that is the only difference we have. There is another term, sometimes we use the removable discontinuity. So, just to define, so the f x y has to be defined at x naught y naught and the limit should exist, and the only difference from the continuity here we have, and this is called removable discontinuity, that this limit is not equal to f x naught y naught. So, it is of course, the function is not continuous, but this is called the removable discontinuity, because we can, by redefining this function value at that point, we can make the function continuous. So, this is a slightly simpler kind of discontinuity which can easily be removed, and we call it as removable discontinuity. Coming to the problems here. So, in the first case we will discuss the continuity of f x y is equal to x square plus y square divided by x y when x y is not equal to 0, and elsewhere this is 0, and we will check this continuity at the origin. So, that means we need to get this limit of f x y as x comma y goes to 0 0 as x y goes to the origin. So, this limit we need to compute, and then we will claim that whether this function is continuous or not. So, if looking at this function x square plus y square over x y, we have already discussed several examples in the previous lecture on evaluation of the limit. So, here also we realize that if we in fact substitute y is equal to m x here, if we fix the path y is equal to m x, this will depend on the path. So, the limit in fact does not exist in this case. So, if we take the path y is equal to m x, this limit will be 1 plus this m square x square. So, m square, and then here also you have m there because of this y. So, after substituting this y is equal to m x, we will get this 1 plus m square divided by m. So, that means this limit depends on path. So, there is a case of non-existence of the limit, and hence the function is not continuous. That is the conclusion in this case, because the limit depends on the path here, and hence the function is not continuous at 0 0. Well, so this is another example of x minus y whole square, and then we have here x square plus y square, x y not equal to 0 0 and x y equal to 0 0. So, at our origin again we will discuss the continuity of this function. So, in this case if we look at this function here, we have in the numerator again x square plus y square minus 2 x y, and here also in the denominator we have x square plus y square. So, all the powers are 2. So, here in the product x power 1 y power 1 makes the power 2. So, in this situation the first try we should make here is by the path y is equal to m x, and see what happens. So, if we go with the y is equal to m x, so here x minus this m x whole square, and then we have x square, and then again m square x square, and this limit x goes to 0. So, what will happen? This limit x goes to 0, x square gets cancelled, we have 1 minus m whole square and divided by 1 plus m square. So, x term gets cancelled, and then the limit is just 1 minus m square over 1 plus m square. So, in this case also the limit depends on the path, and therefore, this function is not continuous at 0 0. So, in many cases, as we discussed before, choosing path itself will tell you that limit does not exist, and therefore, there is no question of continuity for that function. Coming back to this problem, so we have x 4 y 4 over x square plus y 4 power 3 when x y is not 0 comma 0, otherwise it is 0, and we will discuss its continuity at origin again. So, here if we choose this y is equal y square is equal to m x, what will happen? Let us see. So, we have x 4, and then we have y square whole square. So, that means m square x square term, and then here x square again y 4 means we have m square x square term again and power 3. So, what is going to happen now? X power 6 and m square, and here also x power 6 is common, and then we have 1 plus m square power 3. So, we have chosen this path in such a way that all the terms of x square get cancelled, and then at the end we have a dependency on m. So, in this case also the limit does not exist, and therefore, this function is also not continuous. Well, moving further, so we will discuss the continuity of 2x4 plus 3y4 over x square plus y square when x y not equal to 0 comma 0, otherwise this value is 0 basically at the origin, and we will also check the continuity of this function at origin. So, we need to check if this limit is equal to 0. If this limit is equal to 0, then the function is continuous. If this limit does not exist, function is not continuous, or limit may exist and may not be equal to 0. In that case also function is not continuous, but that is the one which we have discussed, removable discontinuity. In that case we call it has removable discontinuity. So, we have to check that what is the limit, whether it exists or not. If it exists, whether it is equal to 0 or to some other value. So, as we see clearly here, we have x square plus y square term there in the expression. So, changing to polar coordinates will be helpful. So, if we change to polar coordinate, what will happen? Here x square plus y square will be r square, and then 2 r4, and then we have cos 4 theta, we have also 3 r4, and then we have sin 4 theta. So, now the r square term will be cancelled. So, here we will have r square, here also we have r square, and then r goes to 0. So, this will limit will become 0. Why? Because here you have r square as a common term, and we have 2 cos 4 theta, and then we have 3 sin 4 theta. So, this term which is sitting with the r square, this is something finite and bounded. Yeah. So, this is bounded because cos is bounded by 1 and also sin is bounded by 1. So, this term is bounded by 5 in fact, and then we have here r square, and when r goes to 0, obviously this will go to 0. So, we are getting this limit independent of any theta. Yeah. So, the limit does not depend on theta, and therefore, this is the limit. So, as we discussed in the previous lecture, that this changing to polar coordinates are very useful often, and like in this case we are getting directly the limit. So, we do not have to check any more, because this is not something we got by fixing the path. If we fix the theta and then evaluate the limit, that is like going through a particular path here, but here the limit does not depend on theta, and we got this number 0. So, this is indeed the limit, and that is equal to the function value. So, in that case this function we say that this is a continuous function. Again we have square root x square plus y square, and then here also square root x square plus y square. We will check this continuity at origin. So, again changing to polar coordinate, because of the reason of the term x square plus y square, we can change to polar coordinates, and then we have r to 0 sin r square square root over square root r square. So, we reduced actually the problem to one variable calculus, and this is limit r to 0 sin r over r. So, this is the case of sin 0 over 0, and then L'Hopital rule we have the cos r over 1, and then the limit r goes to 0 and cos r, as r goes to 0 it is 1. So, this limit is simply 1. Okay. So, the limit exists. So, the limit of this function as x y goes to 0 0 is 1, but the function value at x comma y equal to 0 0 or at origin it is 0. So, the function is not continuous at 0 0, but this is the case what we call as removable discontinuity. So, here we have the removable discontinuity. If we redefine our function here, instead of 0 if we say this is 1, then the function will become continuous. So, this is a removable discontinuity, and this can easily be removed by redefining the function at this origin. Fine. Now, we have to discuss the continuity of this x square plus y square over x cube plus y cube at origin. So, if we change to the polar coordinate again, let us see what will happen. So, though here we do not see any term like x square plus y square which can simplify it, but we still substitute this x is equal to r cos theta, y is equal to r sin theta and see whether it is helpful or not. So, after substituting this we get here r, because here we have r power 4 and then cos square theta sin square theta, here we will get r cube and cos cube theta plus sin cube theta. So, this r into cos square theta, sin square theta, cos cube theta and sin cube theta. Now, the question is whether we can get this limit independent of theta. The answer is no, because this is not a bounded quantity sitting with this r here. This can be unbounded because of this denominator cos cube theta plus sin cube theta, that can also become 0 for some special thetas. So, this is for example, if I take theta is equal to minus pi by 4, then this is getting to 0. So, this is an unbounded term. So, we cannot just let r to 0 and say that this limit is 0. So, here this approach actually is not working out. So, we are not able to conclude anything. However, if we fix theta, then the limit is 0, but we are not supposed to fix theta and get the limit. So, here by changing to the polar coordinate is not helpful in this case, and we cannot conclude that the limit is 0. So, we have to find some paths and see whether the limit exists or it does not exist. So, to check this continuity of this function, what we do, we have to choose different paths. So, one path could be like y is equal to mx and see what is the limit. So, if we put y is equal to mx, we will have here m square and x 4, and then here we have x cube and plus m cube x cube, and then so m square into x over 1 plus m cube. This is what we are getting, and then we will let this x to 0. So, in that case, since there is a x there and we have here 1 plus m cube and there was a m square also. So, when x goes to 0, because this is something which is bounded except for some m, but for all other m's this will go to 0. So, y is equal to mx, this there are several paths. So, along the line if you proceed, you will get this limit 0, but that is not helpful again, because we cannot claim that this is the limit. This is along some fixed paths, and this is a very special path actually which we take, and that is a difficulty in some questions where we cannot find out that which path we should choose, so that this limit is different, or to show that the limit does not exist. So, in this case, if we choose y is equal to minus x e power x, so this also goes to 0 0, x as x goes to 0, y also goes to 0. So, this path is taking you to the origin, and if we substitute this now here for y, so y square means x square e power 2 x, and here x cube minus here x cube e power 3 x. So, this is the special path we have now here. So, x cube and there also we have x cube, and when x goes to 0, so this becomes x e power 2 x and 1 minus e power 3 x, and here this is 0 by 0 form. So, we can apply this L'Hopital rule in this case. So, this is x and e power 2 x into 2 plus we have e power 2 x and then divided by e power 3 x with minus sign and into 3. Now, when we pass this limit, so x goes to 0, this is going to 1, this is 0, so this is going to 1 here. So, we get minus 1 by 3. So, the limit of this function along this path is minus 1 by 3, whereas along these straight lines, or you can pick one path itself, y is equal to x, if not the mx, because there was a situation for some m that quantity may become unbounded. So, we take y is equal to x for instance. So, this is x 4 and here you have x cube plus x cube, and the limit x goes to 0. So, the limit is 0. So, along y is equal to x, the limit is 0, and along y is equal to minus x e power x, the limit is minus 1 by 3. So, there are two different limits along two different paths, hence this limit does not exist and the function is not continuous at 0 comma 0. This is the next problem. So, here we go through the continuity of f x y is equal to e power minus 1 over x square plus y square, and then we have in the denominator x 4 plus y 4 for x y not equal to 0 0, and at origin we have the value 0, and we will discuss the continuity of this function at origin. So, since we do see here x square plus y square, so we change to polar coordinate by substituting r is equal to x cos theta and y is equal to r sin theta. So, by doing so, what we will get e power minus 1 over r square, and then limit r goes to 0. So, instead of x y goes to 0 comma 0 to the origin, we will now take r goes to 0, and in the denominator we have r power 4 because x 4 will be r 4 cos 4 theta, and this y 4 will be r 4 and sin 4 theta. So, by substituting here we got cos 4 theta plus sin square theta. And now this term here cos 4 theta plus sin square theta, we can add here plus 2 cos square theta and sin square theta, and we can subtract also 2 cos square theta and sin square theta. So, first these three terms cos 4 theta, sin 4 theta and 2 cos square theta sin square theta, this will become sin square theta plus cos square theta whole square, because that will be the square of this, that is there already sin 4 theta, then the square of cos square theta, that is cos 4 theta, and plus 2 times the product, that is also there, and then we have this minus 2 cos square theta and sin square theta, and sin square theta plus cos square theta we know this is 1. So, we get 1 minus 2 cos square theta sin square theta in the denominator. Now, we have this limit to be considered. So, what is this limit? Now, look at this. So, we have e power minus 1 over r square and then r 4. So, 1 minus this term, the 2 cos square theta sin square theta, we will multiply by 2 again here and divide by 2. So, we have here 2 cos square theta and then sin square theta, and this term, so 4 in the numerator cos square theta sin square theta will become 2 sin theta cos theta whole square, and 2 sin theta cos theta is sin 2 theta. So, that is half and sin 2 theta whole square. So, now we will look at that what is this limit here with numerator 1 over e power minus 1 over r square, and in the denominator we have r 4 and there is a term 1 minus half sin square 2 theta. So, here we will make use of the sandwich theorem. So, let me just explain that through this example itself. So, we look at the bound of this term here 1 minus half sin square 2 theta. So, this sin square theta will take value from 0 to 1. Well, and then this sin square theta 0 to 1, that means this 1 minus half sin square 2 theta will be bounded by half. So, the value will be more than half and less than 1. So, the total value of 1 minus half sin square theta is bounded below by half and above by 1. So, for r not equal to 0, what we can do now, so either we can say that this term is positive because we have here positive term, here also positive term, and this is also positive because it is more than half and less than 1. What else we can do? We can also take the maximum value of this 1 over, so 1 minus this half sin square 2 theta, that is 1, and that can be replaced
here in front in place of this 0. So, we can also bound this by 1 e power 1 over r square minus 1 over r square divided by r 4, and this is 1. So, if we take the maximum value here, so that will be the quantity here by replacing this 1 will be smaller than this quantity, and when we replace by the smaller value here this half, then we can bound at the upper side. So, here in the lower side either we keep it 0 or we keep it e power minus 1 over r square divided by r 4. So, both will work. So, the upper side we have, when we replace this by half the smallest value possible value of this expression here, then we will get 2 e power minus 1 over r square divided by r 4. And now we will look at this term here, that what is the limit when r goes to 0. So, this is precisely when I was mentioning that instead of this 0 we can also write down here e power minus 1 over r square and divided by r 4. So, at the end we will be looking at this limit, whether 2 is there for instance in this term or 2 is not there in this term, does not matter. Basically we are looking at the limit e power minus 1 over r square over r 4. So, here it is going to, when r going to 0, e power minus this infinity, that is going to 0 and this is also going to 0. So, we can apply the L'Hopital rule, but before applying to L'Hopital rule, let us just simplify this by substituting 1 over r to t. So, in that case this r goes to 0 will be t goes to infinity, and 2 over r 4 will become t 4 into 2, and e power minus 1 over r square will become e power minus t square. So, in that case we have the limit t to infinity, because sometimes this substituting the variables, the expression becomes simpler, like in this case now we have 2 t 4 over e t square, and a similar situation we have infinity over infinity. So, again we can apply now the L'Hopital rule. So, here it will become 4 to the 8. So, 8 t 3, and then we have here e t square and then 2 t. So, this t will get cancelled with here and 2 4. So, we will get 4 t over e t square, 4 t square over e t square, and then again this is going infinity by infinity. So, we need to apply again L'Hopital rule. So, it will be 8 t divided by e t square into 2 t, and this t will get cancelled, and then we have here 4, and as t approaches to infinity, this is approaching to infinity and so everything goes to 0. So, as t approaches to infinity, this limit is going to 0. So, this side we say that this, when r approaches to 0, this is going to 0, and here we have already 0. So, this quantity is bigger than 0 and less than 0. So, this is the sandwich theorem which we can apply now. So, it means that this limit of this term has to be 0. So, using this sandwich theorem we get the limit, and hence this function which was asked for the continuity is continuous, because now the limit is 0 and the function value is also 0. Well, so we reach to the conclusion now. So, we have gone through several examples of continuity, and what we have observed that this changing to polar coordinate is very useful, but we have to be careful, as in some of the examples we have seen that one may conclude to the false limit without observing that the term sitting with r is unbounded. So, there we need to be very careful, and at the end this continuity was absolutely nothing more than finding the limit, and if this limit is equal to the function value at that point, then we say that the function is continuous. So, here we have the references which are used to prepare this lecture, and with this I thank you for your attention.